Hello everyone, I'm Hua Yan from Southeast University, China. In this talk, I will introduce O2O store site recommendation under the O2O model while multi-graph attention networks. My presentation today is divided into following four parts. Now we introduce the first part, introduction. First, let's see how the O2O model works. In this model, a customer can place an order online through an O2O platform, such as Uber Eats and DoorDash. Then the platform assigns a courier. The courier picks up the order from a store and then delivers the order to the customer in a short time, such as 30 minutes. Compared to the traditional stores that only accept orders by in-person visits of customers, the stores under the O2O model provide a great convenience for purchases, especially during the pandemic. In the O2O model, one of the essential problems for new stores is to select a suitable store site in the city. For example, when Starbucks want to open a new store, they need to decide which location as their store site. In this work, we focus on store site recommendation under the O2O model. Existing work of store site recommendation can be divided into two categories, including survey-based methods and data-driven methods. In the survey-based methods, people design questionnaires and interviews to obtain feedback from small-scale volunteers, which may result in biased feedback. In recent years, with available infrastructure such as smartphones, researchers have the opportunity to collect large-scale multi-source data, such as check-in data, review or rating data, search engine queries, and satellite data. Based on those data, they build feature-based machine learning models to identify the site with potentially high profits. However, these methods are mainly designed for offline brick and mortar stores, which are not suitable to solve the store site recommendation under the O2O model, due to significant differences between two types of stores. So let's see the detail of the differences between supply and demand aspect. In the supply aspect, offline brick and mortar stores only depend on factors such as good storage. For example, if storage is enough, customers can buy goods from stores. However, in addition to those factors, O2O stores are also limited by courier capacity in O2O platforms. For example, if the courier capacity could not meet the real-time customer demand, the platform would shrink the delivery scope of stores to reduce the demand, which directly reduces the number of the orders from the stores. In the demand aspect, as the service change from offline to online, the customer consumption behavior also evolves. For example, to ensure short-time delivery, people can't place the order in the faraway stores, which is not limited in the traditional offline stores as people can move in person. Considering new supply and demand pattern, we aim to design a store site recommendation framework for O2O stores. The opportunity for our work is O2O platforms naturally record information for accounting purposes. In the supply aspect, the platform collects courier trajectory, which provides us the opportunity to explore the impact of the courier capacity. In the demand aspect, customer order records, including customer location, provide us the opportunity to explore fine-grained customer preference. Leveraging this opportunity for store site recommendation has the following challenges. For the supply aspect, it is not straightforward to quantify the courier capacity. For example, the naive solution is counting the number of the couriers, but we find this solution can't reflect the actual capacity. This figure shows the number of the couriers every 2 hours in Shanghai. We find the highest number of the couriers appears during the noon rush hour and evening rush hour, which indicates courier capacity is high during these two periods. However, if we add the number of the orders, it means the demand, and the supply and demand ratio in the figure, we find the courier capacity is actually low due to surging in order quantity. In other words, supply is impacted by demand. In addition, it is not easy to modeling the complex relationship between capacity and O2O store site recommendation, because courier capacity dynamically impacts both the delivery scope of store and the customer choice. For example, if the delivery time is too long due to limited capacity, the less chance that customers choose this store, so supply also impacts demand. In addition, in the demand aspect, modeling customer demand is not easy because the relationship between customer demand and site recommendation is affected by multiple dynamic factors, including delivery distance, courier capacity, and historic interaction. For example, if customers want to make a decision between two similar stores, the customers may prefer the closer one because they can avoid a long waiting time. Before getting into the design details, we first state our contributions. We are the first to study the store site recommendation under the O2O model. We analyze the unique characteristics of O2O stores from both the supply and demand aspects. We design a store site recommendation model considering new supply and demand aspects, including a courier capacity model based on multi-semantic relation graph attention network to capture courier capacity, and a heterogeneous multi-graph-based recommendation model where the courier capacity, customer preference, and context features are fused. We evaluate our framework based on 1 month's real-world data sets from Alibaba O2O platform, Ele.me. The data consists of more than 39,000 stores and 23 million orders, and we achieved 12.8% of improvement in NDCG S3 compared to the state-of-the-art methods. Now we introduce the model design part. To address these challenges, we design O2 cycle, which consists of 3 modules. In the first module, we extract features and construct 2 graphs from the courier data, order data, and context data, and then input those features and graphs into the second module and the third module. In the second module, we design a courier capacity model to capture courier capacity embedding, which is utilized as the input for the third module. In the third module, we design a heterogeneous multi-graph-based recommendation model to capture customer preference and the interaction information for site recommendation. Next, we will introduce the detail of the second module and the third module. In the second module, we construct a courier mobility graph to model actual mobility of couriers between regions. Nodes represent regions. It means grids in the city. Edges represent couriers' health mobility behavior between 2 regions. Then we construct a region geographic graph to model geographic proximity of the regions. Nodes are the same as mobility graph. Edges represent two regions are close to each other. Intuitively, geographic adjacent regions have similar carrier capacity, and the regions with mobility relations have some correlation in capacity. So we design a carrier capacity model based on multi-semantic relation graph attention network to capture carrier capacity between any two regions. So first, based on carrier mobility graph, we get the node embedding by aggregating information of mobility neighbors. Based on the region geographic graph, we get the node embedding by aggregating information of geographic neighbors. We concatenate the two aspects as the new node embedding and update all the embeddings. Then, we concatenate the embedding of the any two nodes as their edge embeddings, which represent carrier capacity between two regions. To learn carrier capacity, we reconstruct some factors impacted by carrier capacity, such as delivery time of two regions. In detail, we use MLP. The input is the edge embeddings, and the output is those factors. Finally, we output the carrier capacity into the third module. In the third module, we construct a region and type heterogeneous graph to model the complex relations among multiple views of regions and store types in period T. It has three types of nodes and three types of edges. In each region, there are a number of customers and stores. The customer nodes U represent customers' have consumption behavior in this region. The store nodes S represent stores are in this region. SU edge means that customers U is in the delivery scope of the store S. In other words, the customer U can buy goods from store S. Another node is store type, such as coffee and snack. SA edge means that stores with the store type A are in this region. UA edge means that customers in this region prefer store type A. In addition, customer preference and the interaction between customer and store change over time. We define region and type heterogeneous multigraph to represent graphs in different periods. Based on this graph, we design a heterogeneous multigraph-based recommendation model. It has three steps. The first step is edge attributes fusion. This process is only for SU edge. In detail, we fuse carrier capacity from carrier capacity model with multiple factors including delivery distance and historic interaction. Second, when performing the node-level aggregation, each node aggregates information from its neighbors to update its node embedding. We take the node S as an example. For the target node S, on the one hand, through SU edge and the second-order propagation, we learn customer preference within its delivery scope. On the other hand, through SA edge and the second-order propagation, we capture the high-order interaction information between store and store types. In each aggregation, we design a node-level attention which estimates the importance of each source node by node attributes, edge attributes, and edge type. Because we finally want to predict the SA edge values, it means the order number of specific type of stores in specific region. We fetch the node S and the node A for prediction. Considering different regions and store type generally have unequal importance in different periods. For example, breakfast stores are busy in the morning period, We design a time semantic level aggregation. In detail, we concatenate node embedding of S and A, then utilize a multi-head attention mechanism to calculate the importance of each period. Then we obtain the HAS embedding for order number prediction. Then we introduce the evaluation of our work. We evaluate our framework based on 1 month's real-world data set from one of the largest O2O platforms, E2O. We evaluate the model with both the order prediction accuracy metric, including RMSE, and the ranking metrics, including NDCG and the precision. We compare our model with 3 categories of baselines, including store-side recommendation methods, graph-based recommendation methods, and heterogeneous graph methods. This table is overall performance. Each baseline is presented with 2 settings. In the original, baselines are trained with features defined in the original papers. In adaptation, we add additional features such as choreo capacity, customer preference, and location-based features to the baselines. Overall, our method O2Psych outperforms all the baseline methods and achieves 12.8% of improvement in the NDCG S3 metric. We also conduct ablation study to understand the role of the choreo capacity and the customer preference. Without CO means O2Psych without choreo capacity. In this setting, the choreo capacity model is removed. Without COCU means O2Psych without choreo capacity and customer preference. We remove the choreo capacity model as well as the 2 edges in the region and type heterogeneous multigraph. It means the SU edge and the UA edges. The result shows that choreo capacity and customer preference improve the performance of store-side recommendation. In this part, we verify the performance of our method in different types of regions. We consider 3 types of regions, including all regions, downtown and suburb. The results show that our method generally performs well for various types of regions. Lastly, we introduce the lessons part. We have 2 important lessons learned from this work. The first lesson is store-side recommendation under the O2O model should take the choreo capacity and customer preference into consideration. The second lesson is the various types of stores in different regions are sensitive to different periods. That's all about this talk. Thank you.